So we continue with virtual memory, and we'll go more in detail into the relationship between hardware and operating systems. So how the memory management interacts with memory management unit. Let us restart from this slide. Valid and valid bit in the page table. Of course, if the bit is valid for an entry, what we have here in this field, which is the mapping done by the page table, is the frame number, okay? So if the page is in memory, here we have the frame number. But if it is invalid, what we have instead? Sorry? We have a page fault, but here, what does the kernel put in the page table? Nothing. This block corresponding to this to that page. Okay. So since invalid means that there is that it is not currently on memory, it means that it's somewhere on the backing store on the disk. So here there will be the block of disk where this page, the image of this page is currently. And of course, when a page fault occurs, the kernel can knows that it has to bring into a free frame in memory the page that was missing here. So we saw the memory map mechanism on Monday, and now we examine the copy on write mechanism. The copy on write mechanism allows the kernel to save a lot of memory, because when you do a fork, you should, in theory, create a perfect image of the parent. But this is not necessary, because the code pages don't need to be changed. So the mechanism that is used by the kernel is the copy on write. What does it mean? The pages of the two processes, for example, parent and child, share the same pages in memory, in virtual memory. So that means that there is not necessity to copy this physically these files, pages. Just the page table of the parent and the page table of the child point to the same pages. Now,
if the child process, if the child thread is changed, the parent also
change what? No, wait. I just arrived at the point. So, of course, initially, also the stack pages, everything is shared, okay? Because nothing has changed. Only the process identifier changes. The fork returns in a register A to the parent child identifier and to the child 0. But as soon as one of the process changes the content of a page that is shared, of course, this page has to be copied. So here you see the process. So we have process 1 and process 2, say child, share the same page table, illustrated here as this mapping here. And then process 1 modifies page C. So it means that at this point the kernel has to bring in memory a copy of page C because 1 has been modified. Okay? So this is the page for process C, and the previous one is the page that was not modified by the child. Okay? No? Yes. Look. Here, parent and child share the same page C, but now the process 1 writes on C. Okay? As a matter of fact, it writes on a copy of C because the kernel know that this page is shared. So at this point, the two processes will have a different page table because for the same page C, now the page table points here where an offset has been modified. Something has been modified by the process 1. Okay? So if you write, say, x equal 1 in page C for process 1, this is not modified for process 2. Which
page is shared?
You see?
A, E, and C?
Initially, yes. But after one of the process, in this case, process 1 changes something on a page that is shared, this is modified in this way, or the other way around. So process 1 modifies C, but before modifying C, it is copied, and there is a link for process 2 that goes here. It's not important. By the way, this point, the two processes share as much as possible the other pages that did not change, but have to work on the same, on different pages. Okay? So this is the mechanism for the economy of frame in memory that are, of course, important. So now the problem is what happens when a page fault occurs if there are no free frames in memory. Okay? So, of course, this must be solved by selecting a frame that contains a page that becomes a victim page, because it has to be put on disk to leave a place for the faulty page. Okay, so the frame of memory are all filled with pages, and we have to find a frame according to a strategy. So the problem here is to select an algorithm, a page, and an algorithm for replacement that minimize the transfer time between memory and disk, and minimize the future page faults. How? Of course, talking about future is always a problem because we don't know what could be, which kind of page references could be generated, but we can speculate on the behavior, the normal behavior of programs. So, this is the open the chapter of the page replacement algorithm. So, for the page replacement algorithm, we can exploit 2 bits that I have not mentioned in page table. Valid invalid bit is means presence bit, okay? But the other 2 other bits. The first one is the so-called dirty bit or write bit. So if the page has been modified, the flag is automatically set to 1. Okay? This is an important information because if the frame, the page memory, the frame has been modified, if we want to swap it on the disk, we have to copy on the disk because we don't have an exact copy now on the disk. Otherwise, if this flag is 0, the page has not been modified, so we don't need to do the transfer memory to disk because we have already there this page. So we can exploit this information to select among the pages that are on memory maybe one that doesn't need to go on the disk. The second bit is the access bit, so reference bit. If a page has been referred since an amount of time or since a previous event, okay, so it has been referred, say, in an interval of time, it means that probably it will be used again, okay? If a page is not accessed since a long time, probably it maybe has some data that are not immediately used or that have been already used or contain some initialization code that terminated, for example, okay? So this is a good page for replacement. In particular, if a page has not been accessed and has not been modified, of course, this is a perfect fit because we don't need to copy it on the disk, and we are sure that it will be not referred in the future, in the near future. Okay? So there are several replacement algorithms, but here this slide shows what happens when the pages, the frames of memory are completely occupied. So suppose that this is the situation. We have the pages for, here's written monitor, but it means kernel memory. Then you have 1, 2, 3, 4, 5, 6 frames available for your physical memory. And currently they are allocated for, say, in this case, page 0 is of this process 1 is on frame 3, and this is age, you see. Then page 1 contains this instruction, load M, and this, of course, in memory at frame 4. J is frame 5, and so on. For the other process, page 0 is on frame 6, and this A, and so on. In the backing store, there are still 2 pages, 2 blocks, that have not yet been used. And at this point, the program counter is executing load M, but M is page on page 1 of user 1, that is here, and M is not in memory because it's page 3. Okay, page 3 of process 1. This is invalid. So here we have exactly this address here, this index here. So a page fault occurred, but of course the frames of memory are all occupied. At this point, the kernel must decide which of these pages will be the victim. Okay. Of course, the process that generates the page fault goes in the blocker state, and another process, so in this case, process 1 is blocked, and process 2 may run and continue. The process 1 will be restarted from the same instruction when the kernel brings the page M in memory somewhere in one of these frames, and thus updated this page table. Update means that this invalid becomes valid, and here there will be, say, 2, 3, 5, 6, 7, whatever. Okay, this is the replacement, and so the algorithm for page replacement are several, and as I said, their aim is to reduce as much as possible the page fault of the system. Why? Because we want to avoid many transfer from memory and disk, because this is, as a matter of fact, an overhead, so something that is not useful for processing, but just for administration. And because we have also the traffic of file reading and file writing on the disk. So, to evaluate the performance of a replacement algorithm, typically we study the behavior of the algorithm using the reference string, so-called reference string. So we have a string that tell us which page is referred in time. So in this case, page 1 at the beginning, then 2, 3, 4, 1 again, 2, 5, 1, and so on. Okay. Having a string, we can compute the number of page faults that are generating depending on the size of our memory. Of course, if I have a large memory, the number of page faults running the same programs will be higher or lower? Lower, of course, because the probability of having space for loading a missing page is high. On the other hand, if you have a single page of memory, you will have a page fault probably almost at every reference. Okay, so you don't have a page fault if you run exactly the same page, but normally you will have a page fault going out because the working set of the process typically takes more than one page. So this is the behavior of the page fault, number of page fault as a function of the number of available frames. And as you have imagined, of course, the number of page fault decrease. But what is interesting here is that this behavior, general behavior, is an exponential curve. And the reality is hyper exponential. We will see in a few minutes what does it mean and how important is this fact that this behavior is exponentially decreasing. How we measure the performance of in theory of page replacement algorithm. So this is measured as the frequency of page fault or probability of page fault. As you see here, it depends on the algorithm. So you may have a stupid algorithm or more efficient algorithm, and on the dimension of memory. And of course, it's a weighted mean. So you compute the number of page faults obtained by algorithm A using a reference string W and adding size of memory M. So you compute the number of page faults, divide by the length of the string, and this gives you the frequency of page fault, and you weight this frequency by the probability of the string. So this is the normal definition of the average of this probability. Now, what happens in reality and how the page fault probability or frequency depends on the size of memory that we use. And here enter my previous notation about the hyper-exponential behavior of the page fault frequency graph. So here you see that, of course, if you have, say, a page of one element, we have one probability of page fault, and 0 if we can keep all the pages in memory, okay? So, if the references were random, in reality, we would have a behavior like linear like this, okay? Since the number of page faults would depend linearly on the dimension of memory. But what in reality happens is that this is the normal behavior of page fault frequency for normal programs. What does it mean? So, let us, so depending on the algorithm, you may have an exponential curve that is near to the linear behavior or goes toward the optimal behavior. Okay? How I define the optimal behavior? A strategy that knows the future and so minimize the number of page faults. So if I know the future, I can select as a victim something that, for example, will be not referred or will be referred in the future, far in the future, with respect to the other pages. So this is the optimal behavior that is unfeasible because we don't know the future. But using normal algorithm, we can approximate the optimal algorithm having this kind of behavior. What tells us this graph? It tells us an important thing, also in practice. It shows us that, well, there is this n star point where we have a given frequency of page fault, okay? So this frequency of page fault is on the knee of this, so where the derivative of this curve is 45 degrees, something like this. Okay, so at this point we have the best compromise between the dimension of memory that we allocate to a process and the number of page faults. Why? Because if we give one more page, for example, here, you see that the frequency of page fault decrease as a small decrease. But if I give the same amount, if I don't give the same amount of memory, okay, you see that the increase of page fault is much larger due to the hyper exponential behavior of this code. So there is a point here that we can indicate as the well, optimal point for the trade-off between page fault and memory that we allocate. Of course, if I give a lot of memory to a program, you see that the number of page faults just decrease but a little bit, but it occupies a lot of memory and doesn't allow multiprocessing. Okay, so if I give a lot of space to a program, to a process, and another process has not enough space. Okay, so the goal of any algorithm for replacement is to find this optimal place here, this optimal number of pages that is convenient to give to a process for minimize the number of page faults. Of course, this is again theory that can be, of course, verified with several reference strings, but this is the main concept. Page fault increase a lot if you do something that makes the number of pages given to a process, so the residence set, be lower than the working set. So we call this point the working set for the process. So it must have this number of pages to have a reasonable number of page faults. Okay? If we go down instead, the number of page fault increases. So suppose that you have one program and you run it, and it has its own resident set. Okay? Then you run again the same program. So you have 2 times. If memory is enough, okay, that's okay. But if you are forced to reduce the number of pages that the 2 processes have, of course, not in common, the number of page fault increases. So if you reduce the number of pages, the resident set of each of these processes, the number of page fault increases up to a point where that we call a thresh point, where in practice there is always some page that is missing at every instruction, more or less, because the process if only say 1 page and you have 100 processes, yes.
But in theory, if for example we have enough memory to allocate n star pages to
each process, this is perfect.
For example,
This would be perfect.
We want to run a fork process equal to
Yes.
pages.
You.
Is it better to put it in a queue and run the other 3, or decrease a little?
Yes, the first. Yes, it is better to run the 3 that run at their maximum speed and then run the other, because otherwise the number of page faults would be and both run but at reduced speed. Maybe much reduced speed. Okay, so which is the simplest replacement algorithm that can be the simplest because it's the first one that came in mind and the simplest to implement. It's the first in, first out strategy replacement. So if you consider this reference string here, this is same time of reference, and here we mark where there is a page fault, and we have only 3 frames of memory for this string. So initially the memory is empty, so there is a page fault here, and page 4 is loaded, okay, on frame 1. Now, of course, it remains on frame 1, but for illustration of the first in, first output strategy, I make the hold pages go down in this figure. So the second reference is on page 3, so 3 enters and is the newest. So the first is 4 and comes down. Another page fault occur for reference to page 2. So 2, 3, and 4 are now in memory. Now there is a reference to page 1, another page 4. So this red is selected as a victim, okay, because it was the oldest. Okay, and 1 enter as the newest, and 2 goes down. Unfortunately, 4 has been selected as a victim, but is referred in the next reference, so the next access. So there is another page fault, 1 and 2 go down. Oh, but again, 3 is selected as a victim, and unfortunately, but as you can imagine, it has been selected to show you what may happen if you fail to use a good strategy. So there is another page fault, and for the next page fault, 2 is selected as victim. So in this case, you see that the working set has changed with respect to this, you see? Only page 4 is common. So the behavior of the program is that they have a working set, then the working set moves to other pages, maybe because you call a function or jump to another point of the program, or use other data. Okay, so finally we don't have any page fault because 4 is in memory, then 3 is in memory, no page fault, 2 is not in memory, and 4 that was the one that has been loaded in memory since a long time is selected as a victim, okay? And then there is another page fault and 3 is selected as a victim, and so on. So we have 9 page fault with respect to 12 references, 75% of page fault. That would be enormous for a real program. As you know, this number is extremely low. Now, if we instead have one more, we buy another frame of memory, you have 4 frames, we can see using the same this other reference string that there is an anomaly with this algorithm. The number of page fault increases rather than stay the same or decreasing. So in this case, if you do the same for page 1, 2, and 3, there will be 3 page faults, then 4 gives another page fault, and the victim will be 1, but you refer 1, and so on. So if you do the same frame that I illustrated here, you will see that there are 9 page faults. But if you have one more page, the number of page faults is 10. Of course, the behavior that is shown here is an average behavior. Depends on the algorithm, but for a particular string, you may have this anomaly. The second observation is that given an algorithm, I can select a string that is optimal for that algorithm or a worse one for that algorithm. Okay, so we have to reason on average. This is called the Veladi anomaly. So it means that incrementing the number of frames, so you have somewhere a peak is not continuously monotonically decreasing. The optimal algorithm is an algorithm that can be used as a benchmark. So for comparing the behavior of a feasible algorithm. So an optimal algorithm looks in the future. So in this case, there are many optimal algorithms, but in this case, we replace the page that will not be used for the longest period in the future. For this example, you have 1, 2, 3, 4 page faults. Then, when here there is no page fault, for 5, you have a page fault, which is the page that we will select as victim. Not 1, 2, or 3, but 4, because it appears it will be referred in the future after 1, 2, and 3. Then what happens then when there is 5? Okay, no, I missed 5. 1, 2, 3. 5. 5, yes. This 5 that replace 4. Then we replace 1 that will be never referred after this point. Okay. Okay. This is a figure that shows how, with a different reference string, the optimal page replacement works, but it's nothing interesting. For the same string, the first in, first out replacement will give a greater number of page faults, and we can compare the two algorithms. The rationale behind the first in, first out of the algorithm is that the programs go over linearly, or they do, say, loops that are large. Okay, so they use this page, maybe after a long time they return to use the first page. Okay, so the idea is that the programs are structured in this way. So you have an initialization and you use a set of pages. Then this page will be not used. You go on with another section of the program, and so on. The alternative strategy is considering that programs instead do quite short loops. Short, I mean that use a set of pages that are used frequently in loops. Having this in mind, we can implement instead another strategy that is called the least recent used page replacement strategy. So what does it mean? It does mean that rather than substituting the page that has been loaded since a long time, we select as victim the page that has not been referred since a long time. Okay? So maybe I load page X at this time, but then I refer to this page just the time before the next page 4. Okay? So rather than selecting the page that has been loaded first, I select the page that has not been referred for the longest time. Oh, this seems well, quite simple. So in this case, we have 7, 0, and 1 that give a page fault. Then there is a page fault, and since 0 and 1 has been referred in a near past with respect to 7, 7 is the victim. Okay, but this is exactly as the first in, first out would work. No page fault here, because 3 is missing, and in this case the victim is 1 that has not been referred with respect to 3. For 4 it's always 2, and so on. Okay? Yes?
But if we make the assumption that there are some loops,
Yes.
cannot we use the opposite idea? Because maybe we are going to restart a loop, so the...
Yes, so this is the idea of the short loop. Because if you have several pages, they are referred, and say the pages that are not referred, that belong to another region, they can be selected as victim. So, by the way, since we imagine that we have a short loop, it would be dangerous to select as a victim one of these pages, because we need to bring again in memory a page in a short loop. The least recently used page replacement algorithm has a nice property. This called a stack algorithm, in the sense that if you fill this frame here, this framework here, and compute the number of page fault for the same string that we saw before, well, by chance the number of page fault is greater here than 75, okay, for first in, first out strategy. But if we have one more frame, it is guaranteed that the number of page fault cannot increase. Why? Because you can see that exactly this configuration remain the same, adding a new page. So the number of page fault cannot increase. So you will have the same configuration like a stack, and here another frame. I don't know if yes, this is exactly the same configuration of the previous slide, and we have more chances here to keep in memory one page, so to reduce the page load. What is the problem with LRU? The problem is that the page tables, the frame table, how can I say, for the first in, first output strategy, the algorithm run at every page fault, okay? But for LRU, it runs at every reference. So, because if you refer to page X now, you have to change the stack of the recently used pages, even if there is not a page fault. So it's a big difference, because we know that a page fault occurs maybe once over 1 million of reference, or even more, while the references are at every instruction. Okay, maybe not at every instruction because you stay at the same page, but okay. So LRU is always in some way approximate. It can be implemented with 6 pointers to move one page that is in the middle of an array to the top, but in a way of list management. But of course this has to be done at every reference. Something like this, you see that 7 here goes up in this step. Approximations and real implementation of a replacement algorithm is done with the reference bit and the so-called second chance algorithm. How? It is better to look at this figure here. This is called the second chance algorithm, or the clock algorithm, used also in Unix. So when a page fault occurs, all the reference bits are reset. Okay? Then, going on, without page fault, some pages are referred. These pages are being referred, and the other not. Okay? So, what does the second chance algorithm? It is in evolution of the first in, first output algorithm. So it's fast because it works at every page fault. These bits are set automatically at the references by hardware. So we don't have the problem, and we don't have to manage lists. So what does the algorithm? It starts from a location in this one of these pages, and looks at this bit. If the bit is set, what does it mean? It has been referred. Okay, so it put it to 0 and gives a second chance to see this page to stay in memory. Okay, then it goes on. Also, this page has been referred, so we give a second chance to stay in memory. This page was not referred, so it's selected as a victim. Okay. If all the pages are being selected, are being referred. Okay, so it continues to put 0, 0, 0, and comes back to the first position. So in this case, it performs exactly like first in, first out algorithm or whatever. But you got the idea. So if a page has been referred, we give a second chance to stay in memory. And this is a way of approximating the least recently used algorithm. Because maybe this is the page that has been recently referred. But here we are using the additional information of access or reference. We may have still another, a more sophisticated or efficient strategy using not only the reference bit but the dirty bit or write bit. So this is a configuration like this is the best victim. Why? Because it has not been referred and I don't have the necessity to transfer it on the disk. This is the worst case. So it must be selected only when I'm, well, all the pages has been modified and referred, of course. And, well, these two situations, you may select this, but this implies that you accept the transfer cost on the disk, or even if it has been referred, but you don't have the overhead of transferring on the disk, you may select. This depends on a second approximation of the strategy. Okay, then the other general statement is that normally the kernel the kernel select a page that belongs to whichever process. But another strategy would be to select pages of the same process. With this strategy, we have more freedom. Thrashing, as I said, means that the degree of multiprogramming is so high that this CPU utilization is almost zero, because the kernel spends all the time to swap in and swap out missing pages. So we have a situation of thrashing when this occurs. So in the x-axis you have the degree of multiprogramming, and the y-axis the CPU utilization. Of course, for a system you would like to maximize the CPU utilization, and this happens exactly when you increase the number of processes that run. Why? Because during the wait for an input-out operation, another process may run and the CPU is used, okay? But this is okay as far as you have enough pages for these processes. You reach a maximum at a given degree of multiprogramming, then rapidly the CPU utilization go down, and this point essentially depends on two factors: the dimension of the memory and the speed of the disk. So how fast is the transfer of the disk. So you may compute in a way which is this point. This thrashing must be avoided, okay? Because as you can see, the CPU utilization decreases up to nothing. Okay. Now, the second, this is the nice figure that I introduced by end Monday. So this has been plotted by putting a probe. Here is the execution time for some processes. Here is the page number. Okay. So here you have essentially addresses. So you see here that there is no gray area. That would mean random accesses. But the accesses are quite clustered. In particular, what is nice to see here, the addresses growing. That means a vector, an array is processed one after the other, the entry, and here are the matrices. Okay. By the way, the second important thing is that you see that sometimes there is a region of addresses that is used, and other times other regions. Okay. In near time. So this illustrates perfectly what I call the space and time and locality of programs. Now, the concept of working set, more specified. The objective, as I said, of any replacement algorithm is to optimize the working set for each process. This, of course, cannot be done unless we work on the average. So we define the working set of a process, the number of pages or the set of pages that have been referred in a given interval of time in the past, of course. So, looking at this reference string, if I fix the working set parameter that is a time, an interval of time, in this way, you see that in this interval we have reference to page 1, 2, 5, 6, and 7. Okay, so 5 pages. After some time, the number of pages reduces to 3 and 4 for the same interval. Okay, so it means that this, if we use an algorithm looking for fixed interval in time in the past, we have changed essentially the way of counting the page fault. How? First of all, as you can see here, the residence set or working set changes in time, while in the LRU and first in, first out strategy, the working set was fixed. It was the number of frames that we have. Okay? So the control parameter for LRU and first in, first out was M, time, the number of pages. Here is the time. If we fix the control parameter, that is the delta time, to 4 references, using this reference string, we can do exactly what we need. So in this case, we have these pages in memory. Please notice that here the working set includes 4 pages. Then here there is a page fault. This strategy works at every page fault, and it looks at this say 4 references. 2 is not included, so it becomes a big mistake. But we have a page fault, so it enters. For the next page fault, the victim is 1, okay, that doesn't enter the page fault. And since here we have a page fault just at the next reference, in this case it's 5 that exits, and so on. So this strategy has a variable residence set. So to plot the page fault frequency, we use the average residence set in the axis and the page fault in the y-axis. So the residence set is average is the sum of all these numbers, 40, divided by the number of references, 12. Okay. Again, in this case, we have to approximate the working set mechanism, and this is not done, as a matter of fact, but we have an approximation that is very easy to implement, and it is based on the page fault frequency. So the last replacement algorithm that we analyze and that is used also in practice is this page fault frequency scheme. So in this scheme, essentially we decide a priori which is the level of page fault that we accept. Suppose that it is this 1/c, where c is the time. Okay, but this page fault frequency is this one. Now, at every page fault, we look at the distance with respect to the previous one. Okay? So, if this interval is small, so below, so the frequency is higher than the one we accept, it means that we don't have enough pages in memory. So we add the page in memory, a frame. We add to the working set this page. Instead, if the distance between the last two page faults is large, it means that the number of page faults is lower than our threshold. It means that there are some pages that are not used, so we can reduce the number of pages in memory, and we know that this increases the page fault frequency. So we tendentially want to be here to avoid to have a single threshold that could produce some swapping just because small differences. We use an hysteresis form here. So if the frequency, page frequency is higher than this threshold, we add the pages. If it's lower than this, we reduce the memory. So here in this slide, this illustrated the algorithm. So we have C, that is a time between the two page faults, the last two page faults. So if the time is greater than a threshold, it means that we have few page faults, and if tau is the time and c is the control parameter. So if the time is smaller than the number of page fault is greater than the one we want, so we have to add the page to the residence set of the process that generates the page fault. Otherwise, if tau is greater than c, so it's larger, all pages not referred in the interval can be eliminated from the residence set. At every page fault, the reference bit of all pages is reset. Okay? So that we can select the pages that were not referred in that interval. So let us look at the example here. Hopefully, C is set to 3, and the red one are deleting pages. So page fault here, of course the page fault is at distance 1 that is less than 3, so we add page 4 to the residence set of this process. no page fault. Page fault 3, the difference is 2, so we add the page. Other page fault for 2, the residence set increases. No page fault, no page fault, no page fault. At this point, there is a page fault for page 1, and the distance is greater than 3. So we look at the pages that were referred in this interval. Okay? So only 1, the new 1, and 4. So the residence set suddenly reduces. Okay? And on average, what the reference bit will be reset. Here, 3 is added because the interval is smaller than this, and the same for reference at time 12. So the residence set increases. Here, still is 3, probably is correct. By the way, you got the concept, okay? So if the interval is larger than the preset threshold, we eliminate the pages that were not referred. Otherwise, we add. So memory mapped file, you should have understood that we use this memory, virtual memory mechanism to map in memory the block of disks, and allocating kernel memory is different. So a different form of malloc. So the kernel needs to allocate dynamically some structure, but doesn't use the malloc, as we will see as its own k-alloc, kernel alloc, that uses what? Essentially, the kernel knows the type of structure that it usually needs. Okay, so it can organize the dynamic memory as a function of the dimension of this block. So it knows the dimension of process control block, it knows the dimension of a table, for example. Okay, a block. So it uses a different form of allocation, while malloc must be generic. Okay, don't worry about this. Page size, essentially, of course, small pages allows to reduce the fragmentation in memory, because we know that the last page on average is half full. But what dominates the choice of the page size is the block size on disk. So in modern disk, you have 4 kilobytes or 8 kilobytes for cluster blocks, and so the pages are, and the memory also now is less expensive, and you have gigabytes of memory, so the dimension of the pages is typically of 4 or 8 kilobytes. Finally, about page faults, this is interesting. If you have, imagine that this is not 128, so this would be 2 to 8 and 2 to 8, so 2 to 6 entries in this matrix. But suppose that it has the dimension of large matrix. You know that in C language, the matrices are ordered by rows. So it's like a vector, first row, the second row, and so on. So if we process in this way, the data in an array, so simply putting 0, this would generate many page faults because we are looking at the first element here of every column. Okay, while in this case it would generate exactly a page fault when the row ends. Okay, so when you organize your data, take into account the fact that paging is hidden. If you have a large matrix in C, process it by row, or otherwise transpose it. Okay, that's all.